What if the ground beneath your feet could vanish in seconds, like a trapdoor opening under a perfectly normal street? It sounds like a scene from a disaster movie, but it's real, it's natural, and it's happening more often than you think. Today, we're diving deep into the science of sinkholes. Welcome to EDUx Talks. I'm glad you're here because by the end of this episode, you'll be able to explain why sinkholes form, why some are slow and some are sudden, how scientists detect them before they appear, what you can do to stay safe, and why these holes in the ground tell a much bigger story about water, rock, and the hidden architecture of our planet. Let's start with a clear picture. A sinkhole is a depression or hole in the ground caused by the surface collapsing into an underground void. Sometimes that void is part of a cave system carved by water. Sometimes it's a cavity created by dissolving rock or by soil being washed away through small openings. The surface can subside gradually over months, or it can give way in seconds. And while many sinkholes are natural, humans can unintentionally help them along. At the heart of many sinkholes is a quiet chemical reaction that has been running for millions of years. It's the dissolving power of slightly acidic water. Rainwater picks up carbon dioxide from the air, and even more from soil, where microbes and plant roots are constantly releasing it. That turns the water faintly acidic. Think very weak carbonic acid. When that water seeps down into the ground and meets certain types of rock, most famously limestone, but also dolostone, gypsum, and even salt, it can dissolve the minerals little by little. If you've ever seen a sugar cube disappear in a cup of tea, you've seen a version of this. In chemistry class terms, calcium carbonate plus carbon dioxide plus water transforms into dissolved calcium and bicarbonate ions. That's limestone turning into invisible ions in groundwater. Multiply that by geologic time, and you get caverns, conduits, and the Swiss cheese-like networks we call karst. Karst landscapes are the perfect stage for sinkholes. They're built on rocks that dissolve relatively easily and are riddled with fractures and bedding planes, natural pathways that focus water flow. Those pathways slowly widen into channels. Those channels connect into caves, and the roofs of those caves can eventually fail. If you live in or visit places like Central Florida, parts of Kentucky and Tennessee, sections of Texas, Missouri, Pennsylvania, or regions around the Mediterranean and the Balkans, you're in karst country. You might not see dramatic caves every day, but under the soil, things are constantly reshaping. Now, not all sinkholes are the same. Geologists usually talk about three broad types. First, solution sinkholes. These are the slow burners. The rock is at or very near the surface. There's thin soil, and rainwater dissolves the rock directly. Over years, the surface gently sags, forming a shallow bowl. If you've ever walked across a field and noticed a smooth dish-like depression with a little pond after rain, that might be a solution sinkhole.
Second, cover subsidence sinkholes. Here you have a layer of sandy or silty soil resting on top of dissolving rock. As the rock develops voids, grains of that loose soil slowly trickle down into small openings, a process called suffosion, causing a gradual surface dip. These usually don't surprise anyone. They creep. Third, cover collapse sinkholes. These are the dramatic ones that make the news. In this case, you have a cohesive soil layer, often clay-rich, that can temporarily bridge over an expanding void as water carries soil away underneath. Over time, a hidden cavity grows beneath that hard ceiling. It holds until it doesn't. The moment the roof can't support its own weight, it fails, and the surface drops suddenly. That's when you see a big, steep-sided crater appear out of nowhere. So what tips a system from quiet dissolution to sudden collapse? Physics in timing. Imagine the soil over a cavity as a natural arch. As the void gets wider, the arch has to carry more weight. Meanwhile, changes in water can weaken it. Heavy rain can saturate the soil, making it heavier and reducing friction between grains. A rising water table can add pore pressure that floats the soil, reducing the effective stress holding grains together. Conversely, a rapid drop in the water table, say from intense groundwater pumping, can remove buoyant support underneath, causing roofs to crack. In other words, water is both the sculpture and the trigger. There's also the rock itself. Limestone dissolves comparatively slowly, but forms large, stable caves. Gypsum dissolves faster. Salt, halite, dissolves so easily that in places where there are buried salt layers, you can get huge collapsed structures with very little warning. And the geometry matters. Layered rock and pre-existing fractures create the pathways for water, and the local stress state decides how big a roof span can grow before it fails. Now add people into the picture. Many sinkholes are natural, but our infrastructure can accelerate or mimic the same processes. Leaking water or sewer lines can erode soil day by day until a street caves in. Poorly designed stormwater systems can concentrate runoff in one spot, drilling a hole downward. Overpumping groundwater can lower the water table, undermining support for roofs over voids. Construction vibrations can destabilize fragile arches, and old, unmapped mines can collapse decades after they're abandoned, creating sinkholes that look natural but were born in human tunnels. You can think of it like a delicate ceiling that has been slowly thinned by nature, and then suddenly someone turns on a fire hose right above it. Let's make this concrete with a few cases. In 1981, a cover collapse sinkhole opened in Winter Park, Florida, about 100 meters across and over 30 meters deep, swallowing part of a city block, several cars, and a swimming pool. The area is classic karst, and patterns of heavy rainfall and water usage played a role. In 2014, the National Corvette Museum in Bowling Green, Kentucky, lost 8 rare cars when a sinkhole opened beneath a display floor. The museum sits above a known cave-rich landscape. In 2010, a nearly perfectly circular hole appeared in Guatemala City, dropping a multi-story building straight down. That sinkhole was not karst at all. It formed in volcanic ash-rich soils that were eroded by a ruptured sewer system, a process called piping. Same outcome to the eye, very different science beneath. And around the Dead Sea, thousands of sinkholes have developed as the shoreline receded and freshwater groundwater dissolved underground salt layers. This is a reminder. A sinkhole is a symptom, not a single cause. The geology and the water story behind each one matters. So how do scientists study and even anticipate sinkholes? We start at the surface with mapping. Many karst reasons are already documented, and sinkholes cluster along specific fractures and rock units. High-resolution topographic data can reveal subtle depressions invisible from ground level. From the air or space, satellites use a technique called interferometric synthetic aperture radar, INSAR, to detect tiny changes in ground elevation over time, sometimes just a few millimeters, which can indicate zones of subsidence long before a collapse. Laser scanning, LiDAR, cuts through vegetation to show the true shape of the ground, highlighting the pocket-marked texture of karst. On the ground, geophysics helps us see through the soil. Ground-penetrating radar can detect voids in the right conditions. Electrical resistivity tomography maps how easily electricity passes through the subsurface. Air-filled voids and water-filled cavities show up differently than solid rock. Microgravity surveys pick up small changes in the gravitational field caused by hidden cavities. Seismic methods use sound waves to spot anomalies. Altogether, these tools paint a probabilistic picture. This area is stable, that area shows suspicious voids or soft soils. Hydrology is the other half. We monitor groundwater levels because sharp changes can destabilize the subsurface. We trace water flow using dyes and karst systems to see how quickly a sinkhole connects to springs or caves, sometimes in hours, not days, revealing a plumbing network underfoot. We sample chemistry to gauge how aggressively water is dissolving rock. Higher carbon dioxide in soil means more acidic water, which means faster dissolution. And we simulate scenarios, modeling how infiltration from a new parking lot or drainage change might concentrate water in one risky spot. Now, let's talk safety and signs. Most sinkholes don't open without warning, but the warnings can be subtle and easy to shrug off. If you live in sinkhole-prone areas, pay attention to new cracks in walls or foundations that appear suddenly and widen quickly. Doors or windows that once fit but now stick or won't latch. Depressions forming in your yard, especially circular ones, or small holes where the ground seems to drain away. Fence posts or trees that start leaning for no obvious reason. New wet spots that don't dry out. Sudden turbidity in well water. If you see a small hole forming, don't try to fill it with loose soil. That can just funnel more water downward. Step back, rope it off, and contact local authorities or a geotechnical professional.
Sinkholes aren't only hazards, they're also windows into Earth's plumbing. The same chemistry that creates sinkholes carves out celebrated cave systems. Those caves store and move vast amounts of groundwater that communities depend on. In some parts of the world, water-filled sinkholes, cenotes, provided life and held cultural significance for the Maya, acting as sacred portals and reliable water sources in a landscape with little surface flow. Blue holes in the oceans, submerged sinkholes, record past sea levels and climate shifts. In that sense, sinkholes are storytellers, preserving clues about the history of water, climate, and even human settlement. Let's clear up a few myths while we're here. Are sinkholes bottomless? No. They may connect to deeper cave systems, but they have finite depth. Do they swallow entire neighborhoods regularly? Not typically. The most dramatic collapses are rare. Most sinkholes are modest in size and depth. Are all big holes in cities sinkholes? Not necessarily. Some are infrastructure failures, pavement collapsing into voids caused by broken pipes or undermined soil. Similar look, different root cause. Can we predict exactly when and where a sinkhole will open? Not with perfect precision. We can, however, map risk, monitor ground motion, and identify hotspots where vigilance and engineering make a big difference. Let's zoom back out. The science of sinkholes is really the science of interactions between water and rock, chemistry and physics, nature and human activity. If you change one part, like groundwater levels, you change the rest. That's why droughts followed by heavy rains or new developments that reroute water sometimes precede collapses. It's also why the best solutions are holistic. Know your geology, manage your water wisely, monitor your ground, and design with the subsurface in mind. If you're curious about the geology where you live, check your geological survey's maps and resources. Many regions publish sinkhole susceptibility maps and guidance for homeowners. If you manage property or infrastructure in karst terrain, make geotechnical investigation and long-term monitoring part of your standard toolkit. And if you ever notice the warning signs we discussed, trust your instincts and get it checked. Before we wrap up, here's a quick recap. Sinkholes form when the ground surface collapses into a void created by rock dissolution or soil erosion. There are three main types: solution, cover subsidence, and cover collapse. Water, its chemistry, its flow paths, and its pressure drives the process and often triggers failure. Human activities can accelerate it, but with smart design and monitoring, we can reduce risk. Scientists use tools from satellite radar to ground-penetrating radar, from dye tracing to microgravity, to map and anticipate where problems might occur. And while sinkholes can be dangerous, they're also fascinating windows into the dynamic earth beneath our feet. If you found this episode of EDUx Talks enlightening, share it with someone who loves science, geology, or just a good mystery underfoot. Subscribe for more deep dives into the hidden worlds around us, and let me know in the comments what you want us to explore next. Maybe caves, aquifers, or the secret life of groundwater. Thanks for watching, stay curious, and keep your feet on solid ground, most of the time.